Okay, in this video we are going to continue assignment number 6 from my Calc CD class. We are doing double integrals over non-rectangular regions. Let's see what we can do here. So the first thing I'm going to do is I'm going to pull the bounds off the integral because the directions here are to swap the bounds. So we're going to get x is between 0 and 4, and we know that because it's the outer integral and dx is the outer differential. And then we also have x is less than or equal to y is less than or equal to 4, pulling the bounds off for y values. So what this means is that two of our bounds will be y equals x and y equals 4. So I'm going to draw the region. So y equals x has to be the bottom of the region and y equals 4 has to be the top of the region. And then x will go from 0 to 4. So I'm going to graph y equals x, then y equals 4. And now what I'm going to do is I'm going to just shade this in. So let's do that. And there we go. Okay, so what wants to happen is, so like the given one, you were going like from left to right, bottom to top. X likes to go from left to right and y likes to go from bottom to top. So if y is going to go last, it's going to be the constant bound. So it's going to go from bottom to top. So we're going to have from 0 to 4. X is going to go from left to right, which means we're going to go, this is y equals x or x equals y. We'll go this way. Right, so now we can write down that x is going from 0 to y. We can write our integral, and there's really nothing left to do because we don't know what f of xy is, so we can't evaluate this. All right, let's look at the next one. So same basic directions. What's interesting about this one is we're going to evaluate it, and also the way it is currently given, you can't really do it. Try to find an antiderivative of sine of x over x, and you're going to be stuck if you're integrating with respect to x. What's nice is when you integrate with respect to y, you're not stuck at all because you'll just get sine of x over x times y. So we really have to change the bounds, so let's peel the bounds off. So y is going from 0 to 1, x is going from y to 1. And that means that we have y equals x and we have x equals 1 as bounds that are kind of implied from there. And remember, x goes from left to right. So the left curve will be y equals x, the right curve will be x equals 1. Let's draw this thing. So we have this, there's y equals x, there's x equals 1, shaded in a little bit. And so y is going from bottom to top, which means y is going from 0 to x, right? Because the bottom is y equals 0, the top is y equals x. X simultaneously is going to go from left to right, so x is going to go from 0 to 1. So let's set up our integral using those bounds. So y depends on x, so it has to go first, and then x is constant, so it'll be the last integral that we do. And just make sure you match up your differentials, right? So 0 to 1, 0 to x, sine of x over x, dy dx. So y depends on x, has to go first. It has to be the innermost integral. Now we're going to actually do it. So you integrate sine of x over x with respect to y, and you just get sine of x over x times y. Now, we want to be really careful and say what our bounds are. So I'm going to say y is equal to 0 to y is equal to x to kind of remind myself that I'm plugging in for y values here. And then dx is still going to exist. So we still are doing the integral from 0 to 1. We're going to plug in x for y, and we'll get sine of x over x times the quantity. It'll be x minus 0, right? Plug in x for y, then plug in 0 for y, and subtract. And dx still exists. And now the x's cancel, so we're really just doing the integral of sine of x from 0 to 1. This is a common like Calc 1 type integral. So let's do that. So the antiderivative of sine is negative cosine going from 0 to 1. Plug in 1, plug in 0. We get negative cosine of 1 minus negative, which is plus cosine of 0. Cosine of 0 is 1. And then cosine of 1 is 1. So I'm going to rewrite this. No, sorry. Cosine of 1 is just cosine of 1. There's nothing you can do. So I'm going to rewrite it as 1 minus cosine of 1 because I don't like negative leading coefficients. All right, let's look at the next one, number 39. So we're like skipping a little bit. We have f of xy is equal to e to the x squared, and we want to do the double integral over the region that is shown. So we need to work this out. If you take a vertical line and pass it through the region, the top and bottom curve will never change. If you take a horizontal line and pass it through the region, the left and right curve will switch, right? Between 0 and 1, you get one set of left and right curves, and then from 1 to 3, you get a different set of left and right curves. So the vertical line works for us. So what we want to do is dy first, then dx. So if it's a vertical line that works best, then dx should go last. If a horizontal line works best, then dy should go last. So we got to set this up, which means we need some equations. So y is equal to 1/4 x. Then our top curve is just y equals 3/4 x. Okay, so we know that y is going to go from bottom to top. X is going to go left to right. So left to right for x goes from 0 to 4. Bottom to top for y goes from that bottom line up to the top line. So 1/4 x to 3/4 x. Let's set this up, and then I'm just going to use a calculator to evaluate these to kind of like speed along as I go. Actually, you would need, no, you don't need integration by parts. Like this is a standard integral. So dx will be the outermost integral, so the x bounds, and then the innermost, because y depends on x, will be the y bounds. So here we go. 0 to 4, x over 4 to 3x over 4, e to the x squared dy dx. I'm going to just let the calculator get this. So I got e to the 16th minus 1 over 4. That is just enormous. E to the 16th, huge. All right, let's take a look at another one. It's really similar. F of xy is 1 minus 2x. So you don't have to worry about 1 minus 2x. Like, we don't know what that, well, I mean, that's just a plane, so maybe you do know what it looks like. But you don't need to visualize f of xy. What you really need is the region in the xy plane. You need to be able to come up with that. That's where all the like magic happens when you're setting these up. So again, think about it. A vertical line passing through this region between 0 and 2 has one set of top and bottom curves, and then from 2 to 5 has a different set. We don't want that. A horizontal line passing through this region always has the same left and right curves. So I'm going to finish with dy because the horizontal line, it's horizontally simple is what we would call this region. Vertically simple if a vertical line never changes the bounds. Horizontally simple if a horizontal line never changes it. A lot of regions are both, in which case you'll almost definitely choose dy dx. But in this case, we're definitely going dx and then dy. So we need to write some equations. So this line, if you write it as y is a function of x, which is like the algebra 1 normal thing to do, would be y equals 3/5 x. But because we are going to do dy last, we have to get this to be x as a function of y. So x is 5/3 y. We're going to do that with the other line too. So we have this in terms, y is a function of x, the kind of normal thing to do. We'd get y equals 3/2 x, but we need x as a function of y. So we have x is 2/3 y. And then just looking at it, you can see that y is going to go from 0 to 3. So from 0 to 3 here, we're just going from bottom to top, which is what y wants to do. And then x wants to go from left to right, so this way, which means we are going from the green line to the yellow line. So 2/3 y is less than x, less than or equal to x, less than or equal to 5/3. Okay, let's set it up. So x has to be the innermost integral because the x bounds depend upon y, so you have to integrate with respect to x before you integrate with respect to y. So I will set this up. 0 to 3, 2y over 3 to 5y over 3. The quantity 1 minus 2x, that's f of xy, which again, we don't need to know what that looks like. We just need to just work it into our integral. Dx first, then dy, because this is horizontally simple. I'm going to actually do this one. So let's go back and so we're going 0 to 3. The integral of 1 is x, and then negative 2x is x squared. And then we are going from x equals 2y over 3 to x equals 5y over 3. There is no y in here, so it's not really ambiguous, which is why I didn't write x equals. But usually I will if there's still like y's left over. No y's in this. So it's not ambiguous, right? The only thing you could possibly be plugging in for is x. So I'm just going to do that. So you plug in 5y over 3 for x, and you get 5y over 3 minus 25y squared over 9, minus plug in 2y over 3, so 2y over 3 minus 4y squared over 9. That's all going from, we have to integrate that. I was going to say now we just evaluate it. No. We have to integrate this. I'm going to collect like terms because there are some that you can deal with here, and it just makes it easier. Right, 5y over 3 minus 2y over 3 is actually just y. And then you have negative 25y squared over 9 plus 4y squared over 9. Could not possibly be 7y squared. Oh, yeah, it's 14 for 20. I got you. It's 21y squared over 9, which is 7y squared over 3. There you go. Not a mistake. I always write these out ahead of time so I can walk us through them. And sometimes I get confused. All right, we got to integrate. So plus 1 times the reciprocal in all cases. So 1/2 y squared minus 7/9 y cubed. We're going from 0 to 3. What's nice is when you plug in 0, it's just going to 0 it out. So really, it's just what do you get when you plug in 3? So we're going to get 9/2. And then you have like 27 over 9 is 3. So that's why you just have minus 21. And then ultimately, this is negative 42 plus 9 is negative 33 over 2. And then you can check them on a calculator. Definitely encourage that. Like whenever you set them up, it's especially useful on the calculator when you're going to try to like change the bounds. You can like do it one way and then just do it another way and see if you've done it correctly. All right, we got 2 more in this video. So f of xy is x over y squared. We are not concerned with that because we don't need to visualize that to do this problem. There are some tricky things that could happen, like maybe on the interval you're given, y is equal to 0 somewhere, so this could have issues. Not the case for us. So we have this triangle. I want to do this in one shot, right? So most people's inclination is to go dy dx, but that would mean that a vertical line passing through the region always has the same top and bottom curve. And from 1 to 3, you have one top and bottom, and 3 to 5, you have another top and bottom. So that's not the way to go. Instead, use a horizontal line, and the left and right curves will never switch. That's what we want to do. So we're going to go dx dy, which means we just need to get our bounds in terms of, like, x has to be a function of y. So let's start with this line. So if you write it as y is a function of x, which I think is the way to go, I'm going to use point slope form, get y minus 4 is 1, the quantity x minus 3. I'm going to solve that for x. That's an algebra 1 problem. Hopefully you can work it out. Comment if you need help. And then for the next line, I'm going to color it in green. In point slope form, that's y minus 4 is negative quantity x minus 3. Solve that again for x because we need x to depend on y so that our outer bounds can be y values that are constants. So x is 7 minus y. All right. Y wants to go from bottom to top. X wants to go from left to right. So bottom to top, we are going from 2 to 4. X wants to go from left to right, so that's from yellow to green, which is y minus 1 to 7 minus y. So we're going to set it up with x as the inner integral, and then y as the outer integral. And that'll give us a finite number when we're done. So we set this up 2 to 4, y minus 1 to 7 minus y, x over y squared, dx dy. And then I'm just going to use a calculator again. You can do it by hand if you want to. I don't, so I've used calculator. All right, let's take a look at the next one. All right, so we have f of xy is x plus 1, which again is a plane, but we don't really need to know that. We have this region. A vertical line will switch, right? From 1 to 3, you get one set of top and bottom curves, and then 3 to 5, you get a different set. A horizontal line also switches. Since that's the case, I'm just going to do dy dx, because that's what I would rather do anyway. So we got to get equations for a lot of things. We'll split it here. This yellow line in point slope form, y minus 5 is 2, quantity x minus 3. We're going to solve that for y, but we don't need to get fancy, so I'm just going to say y is 5 plus 2 times the quantity x minus 3 because I'm planning on using a calculator. If you're not using a calculator, you definitely want to simplify that. Let's get this green line here in point slope form. Y minus 5 is negative quantity x minus 3. Again, just solve for y. We also need the blue line. So there's a third line. I said blue before I showed it. We need this blue line. Point slope form y minus 1 is 1/2 quantity x minus 1. Solve it for y. All right. I think we're pretty much ready to go. So for the first interval, 1 to 3, we have x going from 1 to 3. On that interval, y goes from the blue line to the yellow line, right? So I'm going to write down that integral. So we are going from 1 to 3, and then blue line to yellow line, quantity x plus 1, dy dx. Plus, there's no way to do this without two integrals, at least none that I can see. On this interval, so from 3 to 5, for x, y is going to go from the blue line to the green line. So again, I'm just going to write it down. So we will get 3 to 5, and then blue line to green line, and then our quantity x plus 1 dy dx. I'm going to use a calculator again, and I got 24. A good exercise would be to switch the bounds, right? Change the order of integration. and see if you get 24 a second time. But that's it. I hope this was helpful, and good luck.